Okay, now that we have the cosine transform, we're going to take the quick hop over to the discrete cosine transform. But before I do that, I just want to do a little aside. As we start multiplying frequency transforms, I want to do a little aside to kind of relate these things together and show why we would do one or where we would do one over the others. And so in the family of Fourier transforms, we have transforms that are, or we have different situations in which we might find ourselves. Let me kind of put these down. We could have discrete or sampled time domain, or continuous, which would be the opposite of that. And we could have periodic, and we could have non-periodic. And in the frequency domain, we can actually have the same thing. We can have periodic signals, non-periodic signals. We could have discrete, in other words, just specific frequencies are present, or continuous. And so I'm putting together a little grid here to show how all these things work out. So time will be along the top part of the grid, frequency along this part. We'll have discrete and continuous. And this way we'll have discrete and continuous. Okay, so which transforms fit in which places? Well, discrete in time and discrete in frequency is the discrete Fourier transform, the DFT. And so in this one, in time, we are periodic, and in frequency, we are periodic. So the DFT is defined from 0 to 2 pi, or minus pi to pi, however you want to. But then if you evaluate the DFT outside that range, you find that it's periodic because it's made, uses periodic functions to build it up. So if you have discrete in frequency, but continuous in time, then you have Fourier series. And so this is where we were with our cosine transform. In this case, it is periodic in time and non-periodic in frequency. And then down here where we have continuous in frequency but discrete in time, this is the discrete time Fourier transform. And so if you took 2026 or 2025 here at Georgia Tech, we spent a lot of time talking about this one. It's periodic in frequency, but in time it's non-periodic. And finally, if it's continuous in both, we have the good old-fashioned Fourier transform. It's non-periodic in time and frequency. So where does the DCT and the cosine transform fit? Well, the cosine transform is over here. We're discrete in frequency. We use discrete frequencies to build it up. But it's continuous in time over some interval. And here we have the discrete cosine transform that's discrete in both places. Now, one thing to notice, if you haven't already, is when we're discrete in frequency, we are periodic in time. And when we are discrete in time, we are periodic in frequency. Okay, so that's where everything fits. We're going to focus on the DCT right now. And DCT, discrete cosine transform, is analogous to the DFT. And it is a sampled, as in frequency, or time, sampled version of the cosine transform. So since it's sampled in time, we know that it's going to be periodic in frequency. And since it's discrete in frequency, we know it'll be periodic in time from our little table over there. So the DCT basis functions are, we're going to use psi again. One over the square root of n, k equals 0, and 2 over the square root of n, cosine, I don't know if I left myself enough room, n plus 1/2 for k equals 1 up to n minus 1. So it's easy to see that these are orthonormal. So actually, let's just go ahead and see how easy that is to see. Because the transform, since we're now discrete, is going to be a sum. Well, when k and L are both 0, then we're multiplying 1 over the square root of n times 1 over the square root of n, so we get 1 over n. And we add that up n times, and so we get 1. If they are the same frequency, then we will have 2 over n times a cosine squared term. The cosine squared term will sum up to 0 because it's got equal positive and negative parts. And 1/2 times 2 over the square root of n would be 1 over n. So once again, we get 1. I know I've gone through this a little bit fast, and I'm not really showing it. You can take my word for it. If we have different frequencies, then we're multiplying 2 different frequencies, 2 different sinusoids, and we're going over half a period. And so you may recall half a period would be something like, of a signal would be something like psi 1 It still has equal positive and negative parts. We don't have to go over a full period like we do in side 2. But we have equal positive and negative samples, and so when we sum those up, we're going to get 0. So when k is not equal to L. One other thing you may have noticed is this 1/2. Where does that come from? So we tend to sample between where we'd normally sample. We're still sampling evenly. It's just that in effect what we're doing is we're sampling a cosine function with a little bit of a phase offset. And this is one of the characteristics of the cosine transform is depending on how we sample, we get slightly different transforms, and it turns out that sampling at n plus 1/2 tends to work slightly better for data compression. Okay, finally, we should note that we can use the FFT to compute the DCT to speed up computation. So this is actually be a subject of homework or something you can do on your own. But we can talk a little bit about that. How would you go about figuring out how to use the FFT? Well, think about it this way. We're going to go back and look at the cosine transform. The cosine transform is derived from taking a symmetric extension of our signal and then doing a Fourier series on that. Okay, so in the case of the cosine transform, the Fourier series comes from the fact that it's continuous time. So if we have a discrete time, we could do a symmetric extension, and then we would end up doing the discrete Fourier transform on our symmetric extension. Now there's one other problem that comes in, and that is this 1/2. So what do we do with the 1/2? Well, the 1/2 comes out to be a phase term. So if we do a symmetric extension and we apply the appropriate phase shift so that the equations all look out right, then we can express our DCT transform, our discrete cosine transform, in terms of a DFT transform, and then we can use the fast Fourier transform to fix it. So that's going to be one of the homework assignments, and next we'll talk about the two-dimensional DCT, or we'll start with the two-dimensional cosine transform and then go to the two-dimensional DCT. Thank you.